Hello guys, it's Mr. Fuzzy Penguin. In this video, we're doing something a little bit different from my conventional math equation videos that I typically put on this channel. Because today is Pi Day, and I typically do something a little bit special for Pi Day. Now, in this video, I'm on a bike, traveling at some unknown speed. And my goal is to use a fast Fourier Transform to find out what speed I am traveling on this bike. And if you're curious as to how I could do that, stick around to the end of this video. Alright, so the whole premise as to how I'm going to measure the speed of my bike is quite interesting. And I'm going to explain how I'm going to do that. So over here is the XC27 North Rock. It's a pretty nice bike, had it for about a year. But as you can probably tell, the tire is pretty worn down the middle. And that indicates to us that the tire will typically hit the grooves against the pavement very, very frequently. Now, this is actually very useful for us because if we can somehow get the frequency of the tire grooves hitting the pavement, then we can actually find the speed of the bike very simply, right? We can do that because we can find the entire circumference of the tire. And after that, if we know the frequency from the grooves hitting the tire, we know that is one groove out of the number of grooves around the tire. And we can deal with the math and get into the weeds of that more later. But first step is actually going to be to measure the distance between the grooves. And the second step is to count the number of grooves on the tire. Well, I don't have all day, so I'm not going to go ahead and do that. However, what I do have is a bunch of twigs lying on the ground. I happen to find this twig over here, which is about the same length as the distance between each groove on my tire. So that is pretty useful. The second problem that we have to tackle is counting the number of grooves. Now, I am lazy and I don't want to do that, but I'm also an engineer, so I like to approximate and find smarter solutions to impractical problems. So here is 27.5 inches indicated on the tire and 2.2 inches as the width of the tire. This tells us that the diameter of the tire from here all the way down to there is 27.5 inches. That means that we actually know the circumference because pi times d is equal to the circumference of the tire. Now, if we know that this is one twig length, then we can actually go ahead and measure the length of this twig. We can measure the length of this twig and then divide it from the circumference of the tire, which we're going to use pi in order to calculate it, so happy Pi Day. We're going to know the number of grooves on this tire. And if we use a fast Fourier transform from an audio recording of the tire hitting the pavement, we can get a frequency. And the reason why we get that frequency is because whenever we're biking, this groove of the tire will hit the pavement first, followed by this groove, followed by this groove, followed by this groove, followed by this groove, and the rest. So what that typically looks like is it's going to look like a waveform where it's 0, 1, 0, 1, 0, 1, 0, 1. That digital signal or impulses that happen consistently throughout time in a discrete measurement will yield a frequency. So that's what we're going to be measuring today, and let's go ahead and do that. I also want to say one more thing. If you are ever to do this experiment, it's a pretty self-explanatory experiment, it's pretty easy to do. Please do it in a safe environment. So over here, I'm actually in a parking lot. It's a pretty empty parking lot. There's not many cars going on over here because everyone's left for spring break. So again, if you ever want to do it, wear bright reflective clothing, do it in broad sunlight, and also, most importantly, don't forget to wear a helmet. These things save lives. Wear a helmet. So, have fun and let me know if anybody's ever done this experiment. It's been an ongoing challenge for me to find how fast I'm traveling on my bike, and I'm pretty excited to do this. So, let's do it. Alright, so here we are. We have a twig and we have the ruler. So, let's go ahead and measure this in centimeters. So, over here, very conveniently, happens to be exactly 3 centimeters. Look at that. That's really nice, right? Now, let's go ahead and find the number of grooves on the tire. In terms of calculating the number of grooves on the bicycle, it's a lot simpler to do a little bit of unit conversions rather than counting physically the number of grooves, because we are going to do a little bit of estimation work anyway. So here's how we do it. We know that one twig is exactly 3 centimeters. We also know that there is a measurement to be converted here. Centimeters can be converted to inches. So that is how we would get it in inches. So the 3 centimeters, or the length of the twig, is about 1.181 inches. Next, we're going to go ahead and use the bike wheel's diameter. Now, in order to find the circumference, we just multiply by pi. Next, we divide it. Taking the floor of that, we get about 73 twigs, or about 73 grooves on the tire. So from that little experiment that we just did, there's a particular note that has been played, and we're going to do an analysis with fast Fourier transform later. But the note in particular sounded something like this. So although that wasn't a really stable wave, it had a little bit of fluctuations. What I'm hoping is that the frequency, when we do the frequency domain analysis, we'll have a spike, and that is like the majority of the wave is represented by that single spike. And we'll see how much noise is involved, because as earlier from that recording, there was quite a lot of wind and other external factors. So we'll see how that turns out. So here's the code that I have in order to plot the fast Fourier transform of the wave file. The wave file is imported over here. There's a sample rate to know how many samples are taken, the audio data itself, and we just check simply if it's a stereo or a mono channel. In this case, it's a stereo channel, so we're going to use twice. Now, we have the length of the audio data, which is the number of data points that we'll have, and here we have the actual fast Fourier transform being conducted, and the frequency of the fast Fourier transform on the x-axis. The whole plotting is being done over here. The x label is labeled to be frequency, and amplitude or magnitude for the y-axis. This is just some titles to make it look nice, and some grids to help us see some things. So, this is what happens when we run it. Alright, so over here we can see that this is the output of the fast Fourier transform of the wave. So let's go ahead and interpret this one step at a time. What's happening over here? Well, the most important thing is that we're going to be looking at this particular region, the highest part of the wave. The reason why we don't really care about all the stuff down here is because all of this is really just a whole bunch of wind. This was actually one of the major challenges that I bumped into while trying to record a good audio clip to serve in this video. It was because it was such a windy day that all of this noise, yeah, that's just noise, that's just wind. So we're not going to look at that. And the reason why we're not looking at this particular range of frequencies is because this is so high that we can just kind of disregard it. Alright, so with that being said, I'm going to take a look at only this particular region, the top part. So what's happening over here? And why do we see 3 peaks? What do these 3 peaks represent? So firstly, let's talk about the highest peak. The highest peak here is without a doubt going to mention the loudest, because amplitude denotes how loud the wave is. It's going to denote the loudest frequency, the most prevalent buzzing noise that we hear. That is actually what we're looking for. That is the velocity of my bike. Alright, hooray, we're done, let's move on. Well, not so fast. I actually kind of want to talk about what's happening over here and here as well. So over here is a pretty low frequency. Again, you can see that it's about 85 or 86 hertz. So what is causing that low frequency? In fact, if you were to hear a wave of 85 hertz, it would sound like a low rumbling noise. It would sound like this. So again, what's causing that? Well, that is really hard to answer. There's quite a few culprits that might cause a rumbling noise. The rumbling noise might be caused by the chain. It might also be caused from the gear. It could have been caused even by the broken reflector light in the front of my bike clanging against the handlebars. I have no idea. Regardless, this low rumbling noise is definitely not the tires. It's just a whole bunch of other things that are kind of clashing together. And that's what makes this really, really elegant. The fast Fourier transform can find all sorts of frequencies that we may not even have considered. So what about this one? There's other peak that's also fairly high. What's going on? In fact, this is 575 Hertz. If we were to listen to it, you can see that it's a little high. So again, what's causing that to happen? Well, the reason why this happens is because of just some human error. What do you mean human error? Well, essentially, when I was biking, I was kind of getting a little bit tired because I was going uphill, and it was also because there were so many takes. Now, unfortunately, whenever you're biking and you start to get a little tired, you start to kind of wobble a little bit. Biking and tilting to the left and to the right, you start to wobble a little bit. Maybe it's not that obvious, but you can go ahead and replay the video and you'll see it. I definitely wobble a lot. Whenever that wobbling happens, a little bit more grooves on the side of the tire are introduced, and they too strike the pavement, meaning that when I turn to the left or turn to the right slightly, 2 times as many grooves are hitting the pavement at any given moment. That is why the frequency is nearly double. And you can also notice that with this slightly doubled frequency, that the note sounds exactly the same, but with different pitches. These are called octaves. They're also commonly known as harmonics. So that's probably what's causing it, although I can't be too certain. Regardless, it's still very interesting to see how the Fourier transform was able to pick up such frequencies that we, again, probably definitely did not consider. In fact, I was only predicting that the wave would only have just this. But I probably should have known that there would be noise, such as wind and whatnot. But still a very, very cool tool nonetheless. Now, without further ado, let's take our value, about 285 Hertz, of the tire striking the pavement, 285 times per second, by the grooves, and we can do a little bit of math and actually calculate how fast my bike is traveling. So from the earlier fast Fourier transform, we were able to get the information of our bike making a 285 Hertz sound from the tires hitting the pavement. This of course is happening because the grooves are hitting the pavement 285 times per second. This is a pretty silly unit of measurements. I mean, no one really says that I traveled 285 twig lengths per second. The length of the twig was 3 centimeters. So if we were to convert the unit, it would look something like this. Converting the centimeters into meters, we would get that. And this, if we were to calculate it, would give us meters per second. Let's instead use more conventional units of measurement, such as kilometers an hour. So if we were to multiply this, and multiply another scale for the seconds and hours, we would get kilometers per hour. Multiplying another scale that converts miles and kilometers, we can get miles per hour. So these values, 30.78 kilometers an hour and 19.083 miles per hour, was the velocity that my bike was traveling at. Alright, so I hope you enjoyed this video, and I will see you in the next one. Goodbye.